So in our first calculus lesson, we're going to look at slopes of tangents. And one thing that you should know going into this course is the difference between a tangent line and a secant line. When we're talking about a curve, so here you have a green curve, okay, graph of a function. The secant line, the blue line here, is a line that connects 2 points. And if you look at the slope of that secant line, that tells you the average rate of change of the green graph. Of course, curves don't have slopes. Their slopes or their rate of changes are constantly changing depending where you are in the curve. For example, here, the rate of change is negative. Okay, between the 2 points on the secant line, clearly the rate of change is positive because the graph is increasing, but it doesn't increase at the same rate. So a secant line will give you the average rate of change. A tangent line is a graph that just touches the curve at one point. We can kind of think of it as touching the curve at that point, but not necessarily crossing the curve is one way of thinking about it. The tangent line represents the instantaneous rate of change at that point. So on the green curve, the slope of this tangent line will tell you the exact rate of change at this point. And then of course that rate of change changes as you move along the curve. Now, in this course, we're going to look at what's called differential calculus. In differential calculus, it talks about rate of change of curves. So the whole goal of differential calculus is to talk about how we can find rate of change of a curve. Now, obviously, it gets a little bit more complicated than that, but that's what we're going to look at. As an example, I've got the graph f of x is negative x squared plus 4x plus 1 is shown here, and I've actually labeled the point 3, 4. And the goal here is, suppose we want to know the rate of change of this parabola at the point 3, 4. Clearly, we can see that that rate of change is going to be negative because the graph is going down. Now, from our work last semester or last year, depending on when you took advanced functions, you should be familiar with the idea that what we really need to do is we need to find the slope of the tangent at this point right here. And there you can see drawn a tangent line in there. So the goal is to find the slope of this black line. And last semester or last year, we talked about the fact that in order to estimate the slope of the tangent, what we need to do is we need to look at slopes of secants that are very small. So although that's really the only way we're able to do that. So let me pull up Desmos and show you what I mean. Okay, so what you should see now is the exact same graph in Desmos with the blue tangent line drawn. So in order to calculate the slope of this blue tangent line, we're going to start looking at slopes of secants. So secants that join 2 points. So let me do that. Okay, so here's a green secant line now. So again, keep in mind that at x equals 3, our goal is to find the slope of the tangent here. So notice what happens as I move this point in and I create a smaller and smaller secant line, the slope of the secant line gets closer and closer and closer to the slope of the tangent. And that's true from if we start before the point x equals 3. It's also true if we go after x equals 3. So the slope, you can see the slope gets closer and closer to the slope of the tangent. And that is basically the goal in calculus when it comes to calculating the slope of a tangent line, is to come up with the smallest, notice it disappears for a second there when I put it right on, is to calculate the limit, it's called the limiting slopes of secants. So one method to find the slope of the tangent at x equals 3 would be to calculate slopes of secants that are between the point 3, 4 and points that are very close to that. Now notice that down here I've written 3f of 3. Get used to that idea, okay? X equals 3 and this point is 4. If you plug in x equals 3 into this equation, you get f of 3 is equal to 4. So sometimes we just talk about the point 3, 4 as being the point 3, comma, f of 3. Now f of 3 does evaluate to 4. So that's what we're going to do next. And you've probably done something, you should have done something like this before. So this should be a review. I'm going to use a table to do it. So I'm going to look at some very, very small secant lines. And when I say small secant lines, I mean secant line connects 2 points. So I mean, when I say small, I just mean the points are close together. So I want to look at points that are close to 3, 4 and calculate the slope. It's like you're calculating the average rate of change for just a very, very small part of the graph. So to start with, keep in mind that the slope formula is obviously necessary here, the y2 minus y1 over x2 minus x1, or delta y over delta x. So to start with, I use the point 3, 4, and then I said, well, let's just start at x equals 2. What happens if the secant line goes from x equals 2 to x equals 3? Well, you can see that your points would be 3, 4, and 2, comma, f of 2. Now, f of 2, I've already figured it out, is equal to 5. So really, it's the point 2, 5. Okay, so 5 minus 4 divided by 2 minus 3 would give you a slope of negative 1. So that's the slope of the secant that goes from this point right here to this point right here, which is obviously not a good estimate. Okay, I mean, that slope is definitely, that slope is negative 1. We can see that this slope looks like it's a lower slope than that, or a higher negative number, bigger negative number. So let's move closer. Instead of 3, 4, let's try using x equals 2.9. So that would be like a point that's like right even here. It's hard to draw even. Okay, so the secant that goes from here to here. What do we get when we do that? Well, we use 2.9 and f of 2.9. Now f of 2.9 is 4.19. So really we're dealing with the point 2.9, comma 4.19. And that gets us as a slope of negative 1.9, which is quite a bit different than negative 1. And obviously closer to the slope of the tangent line. And I did one more example. I did 3.1. Just to point out the fact that you don't have to look, your secant doesn't have to start before the point, it could start after the point as well. So I use 3.1 and f of 3.1. So really 3.1 and f of 3.1 I calculated to be 3.79. Okay, now we do our slope calculation. We do need to be a little bit careful here. It's 3.79 minus 4 divided by 3.1 minus 3. So in this case, the denominator is positive and the numerator is negative, which still gives us a negative number of negative 2.1. So these last two really give you a good idea as to what the slope of that tangent is going to have to be. The secant line that goes from x equals 3 to 3.1 has a slope of negative 2.1, and the secant line that goes from 2.9 to 3 has a slope of negative 1.9. So I think we can say pretty comfortably that the slope of this tangent line at x equals 3 is equal to negative 2. Now, as it turns out, it is exactly negative 2. That we will worry about later. For now, you can just say it seems like, or a good estimate is negative 2. Now, I know that a lot of you would look and say, oh, well, if it's negative 1.9 and negative 2.1, it must be the average of those two. Yeah, and that's true for quadratic functions. This is a quadratic function. It's not necessarily true for all functions in general. So just be a bit careful with that. I think the next part of this lesson, you might find this a little bit complicated as I go through these steps, but at the end, I think it will make a lot more sense. I think when you see the end result, even any trouble you have with this might not be so bad. Okay, so in this table, each time I used basically the slope formula, and you should make sure that you understand these calculations here. Okay, so starting with the slope formula, however, our point x1, y1 was always the point 3, 4. We always use that as one of our points because we were looking for the slope of the tangent at that point. So we can replace x1, y1 with 3, 4. So we get that right there. Now, I also took y2, pardon me. Instead of using y2, I used f of x2 because really the function was given in terms of f of x, not in terms of y. And we should be comfortable with the fact that y2 is really the same as f of x2. Now, the goal was to pick an x value that was very close to x1 or very close to 3. So what we do now is we introduce a small number, and we do call it h, and h is always what's used in the calculus. And we say that x2 is really 3 plus h. So x1, which was 3, okay, I should write that in. And our number is just 3 plus a little bit, or minus a little bit, because we could say that h could be negative as well. So instead of having x2, we could just say x2 is really 3 plus a little bit. Like, for example, here, it was 3 plus 0.1. Here it was 3 take away 0.1. Here it was 3 take away 1, which is quite a bit. It's not a very small number. So really in each case, here for example, we have the 0.34. Plus h, and f of 3 plus h. So in each case, we could think about that point as really being just the number 3, but plus or minus a small number, and then whatever you get when you put 3 plus h into the equation. For example, how am I getting 3.79, by the way, is I'm taking my x equals 3.1, and I am just plugging it into this equation up here. I'm not showing that work right now in the video. Okay, so if we let x2 equal 3 plus h, then this formula here, our slope formula, turns into this right here. F of 3 plus h minus 3 over 3 plus h take away 3. Now look at the denominator here. Notice that the 3 and the negative 3 do cancel out, and we just get h. So each time in that table, my last column where I'm calculating the slope, this is really the calculation that I'm doing. We can go back and look at that table again and see that. Okay, that here we really just did, each case was f of 3 plus h, take away f of 3, or take away 4, all divided by h. And as I say that, I notice this mistake that I've made here. Sorry, this should be a 4. And 4 right there. My apologies. Okay, I'm going to try to correct that on the handout before you get it. So hopefully yours looks different. Okay. Now, h is a very small number. In fact, we want to make h as small as possible, which is exactly what we did here. We made h equal to, well, I guess -1, and then -0.1, and then 0.1. Our next step might have been to do 3.01, and then 3.001, so making h very, very small. And so that introduces the idea that h is getting closer and closer to 0. And then we can then add in this idea of, rather than just saying, again, that should be a 4 there. Rather than saying, f of 3 plus h minus 4 divided by h, we can say the limit as h approaches 0 of this amount. Now notice you can't actually just say h is equal to 0. As soon as you put h equals 0 here, you've got f of 3, which is 4, minus 4, which is 0, divided by 0. You can't divide by 0, and certainly you can't do 0 divided by 0. So this idea of we would love it if h could be equal to 0, but we can't make h equal to 0. That's just not allowed. We just have to make it as small as possible. And that's the idea of a limit. Now you should have seen this symbol before, limit as h approaches 0. We did a lot of limits as x approaches infinity, and talked about end behavior last year and stuff like that. There's a lot more in limits coming up. So I've chosen to introduce some calculus ideas first, and then we're going to go right into limits, probably tomorrow even. So we'll work with that quite a bit. So instead of making a table of values, we could have just started with this equation, which again I have to keep correcting here. And now if I take, so f of x is equal to negative x squared plus 4x plus 1, that's our equation, okay? So f of 3 plus h, if I replace x with 3 plus h, I get this mess right here, okay? And this is kind of ugly looking, and we're going to deal with that kind of stuff a little bit. And then what I could have done instead of making the table is I could have just figured out, well, what does this do? What happens to this equation as h gets really small? I could just plug in some very small h values, and I would find that I get an answer that this gets very close to -2. So you might start by putting h equals 0.01 or h equals -0.01. Maybe after that you try h equals 0.0001. Anything like that. As long you can't sub in h equals 0, but you can certainly sub in any numbers that you want that are close to 0. So really, this right here is actually what I did when I made the table. I just kind of broke it down into steps for you. I calculated the points separately, okay, and then I put them in here, as opposed to looking at sort of all in one calculation. And later on, we're going to see that we can evaluate expressions like this without the needing to guess. Okay, obviously guessing isn't great. There's a way to become quite confident that we know that this expression is actually equal to -2. This actually isn't a very difficult one, but I'm going to leave it for now. we could actually algebraically figure out why this has to be equal to 2. Okay, so just to summarize again, we found that the slope of the tangent for the graph f of x at the point 3, 4, or 3f of 3, was given by this equation right here. The limit as h approaches 0, f of 3 plus h minus 4 divided by h. It's kind of like you're calculating the slope being delta y over delta x, where your delta x is getting as small as possible. So the points are getting as close together as you can possibly make them. Now, obviously, we don't always want to know the slope of the tangent at x equals 3. We want to know it at any point. So let's, instead of saying the point 3, 4, let's replace 3 with a, and then the 4 would become whatever f of a is equal to. And then f could be any function. It doesn't have to be the function that we were looking at. And that gives us this very important equation right here, which I will try to walk through. And if understanding this equation is really all you need to get out of this. If some of the algebra I did over here, I mean, this should make sense, but if it's a bit confusing, you want to make sure that you understand this for sure. The slope of any tangent at the point x equals a, or at the point a comma f of a, is always going to be equal to the limit as h approaches 0 of f of a plus h minus f of a all divided by h. And let's just talk about that a little bit. So on this graph, I've got the point a. We want to know the slope of the tangent at this point. In order to calculate that, we pick a point as close as we possibly can, which is a plus h, because h is this value that we want it to creep towards 0, if you can think of it that way. And then the y value is whatever you get when you plug a plus h into whatever equation you have. So if I look at that, this is my secant line that's getting smaller and smaller. Okay, here is the run, here is the rise. Okay, the slope is equal to rise over run. In this case, our run is a plus h minus a, which is just h. So there's our run, and sure enough, it's in the denominator. And then our rise is the difference in the y values, f of a plus h minus f of a. So this calculation here, ignoring the limit, is calculating the slope of a secant from this point to this point. Now we have to imagine, though, that h is sort of decreasing, or making it like as small as we can. You know, they're far apart on the graph just so you can see them. So the limit as h approaches 0 says you try to squeeze this in as close as you can and see what happens to these values as you do that. And that will give you the slope of the tangent. Okay, let's start another example. So now we have a different equation. We have f of x is the square root of x minus 1. I just picked that as an equation. And we want to know the slope of the tangent at the point where x equals 5. That will tell us the instantaneous rate of change of this graph when x equals 5. And I've included the graph for you to look at right here. Okay, and notice that at x equals 5, the y value is 2. F of 5 is equal to 2. You can use the equation, although technically you can see it right. Oh, I'm sorry, got that wrong. F of 2 is not 5. We're looking at f of 5. F of 5 is equal to 2. You can use the equation, sub in 5 minus 1, take the square root, you get 2. And our goal, of course, is to find the slope of this tangent line, which will give us the rate of change. In fact, I've actually gone further and said, fine, that's a line, it has an equation, find its equation as well. Okay, so again, taking this definition from above, okay, and then our a value here is equal to 5. So what we're going to do is we want to find the limit as h approaches 0 of f of 5 plus h minus f of 5 all divided by h. Now f of 5 is equal to 2. Or actually what I've done here, sorry, is I've taken the equation, okay, I've taken this definition, I plugged a equals 5, because that's my x value that I'm looking at, and I get f of 5 plus h minus f of 5, and then I've actually used the equation, and I've plugged it in, plugged the equation in right here. Okay, simplify it a bit. Well, 5 minus 1 is 2, we already knew that. Okay, I did that up here as well. And then what we get when we do 5 plus h minus 1 is we actually get the square root of 4 plus h. It's not the square root of 4, which is 2. It's the square root of 4 plus that h value that's getting smaller and smaller. And now what we need to do is we need to figure out how does this behave as h gets really, really small. Notice again, you can't plug in h equals 0. If you plug in h equals 0, you'd have the square root of 4, which is 2 minus 2. You'd have 0 divided by 0, which is, that's called indeterminate actually. It doesn't tell you anything. Okay, you can't divide by 0, and you certainly can't have 0 over 0. So what I did is I just plugged in some small h values. I tried h equals 0.1, and I found out that this equals 0.248. I then tried the other side. H equals negative 0.1 will give me 0.25158. And so I know that my real answer is probably in between those. In fact, it has to be in between those values. So the slope of the tangent here is probably about 0.25 or a quarter. As it turns out, it is exactly a quarter. And most of the examples that we'll do to start this course, it's going to work out nicely like that. Okay, I picked a nice value to work with. X equals 5 is a nice value to work with, and this is actually a nice equation to work with, so that you can determine that it's exactly a quarter. We're gonna need some more work with limits to really know for sure why this is exactly 1/4 and not some other number that's close to a quarter. And not all of these calculations work out that way, where you can tell exactly what the slope of the tangent has to be. Okay, so going from there. We've got the slope. We know the slope of this line is a quarter. The second part of this question said find the equation of the tangent. So we're going to do that next. So to start with, we know that this is a line that has a slope of 1/4, and it goes through the point 5,2. So we have a slope and we have a point. Now 5,2 is often called the point of tangency on the curve. It's a point that the curve and the tangent line share. Since the tangent line is linear, it has the equation y equals mx plus b. Sub in m equals a quarter. And then sub in the point 5,2, and we're just going to solve for b. Okay, 5 times a quarter is 5/4. 2 minus 5/4 gives you 3/4. Okay, 2 subtract 1 1/4. Therefore, the equation of the tangent line is y equals 1/4 x plus 3/4. And there you go. Now, it is very common, though, to write tangent lines in standard form as well, which is ax plus by plus c equals 0, where a, b, and c are all integers, and a is also greater than 0, a isn't negative. So to do that, I can rearrange this. Okay, I bring everything to the left side, so it's equal to 0. And now to get rid of the fractions and make these a, b, and c values integers, I just multiply everything by 4. And since I want a to be positive, I'm actually going to multiply everything by -4, which gives me x minus 4y plus 3 equals 0. So there it is in standard form. Now, in calculus, we find equations of tangents quite a lot. And you notice that this is a lot of calculations here. So there is a shortcut to doing that. And this is something you might have learned. I certainly teach this in grade 10. I don't know how well you remember it or not. And that's using the point slope form. M equals y minus y1 over x minus x1, where m is the slope of the line, y and x are any points on the line, and then x1, y1 is like a specific point that you have. So that looks like this in this example. We have a graph with a slope of a quarter and a 0.25. And the reason that this works is you're basically saying, look, I have a 0.25 on my line. Okay. For any other point on the line, if I were to calculate the slope between x, y, and 2,5, I know that it has to be equal to a quarter. So I know that the rise, sorry, that should be 5,2, not 2,5. I'll fix that. I know that the rise is y minus 2, and the run is x minus 5, and I know that that has to equal a quarter. And it's very easy to get this equation in standard form, because all I need to do now is cross multiply and solve. X minus 5 equals 4y minus 8, or x minus 4y plus 3 equals 0. So look how easily it is once you get to here, okay, and you know that the tangent line is a slope of a quarter, and you know it goes through the 0.52, rather than doing all this work here to get to here, it's much, much quicker just to do this right here. 1, 2, basically 3 steps, and you've got the equation of the line. Let's do one more example that's very similar to this. Okay, so in this example, I've chosen to work with the curve y equals 1 over x, and I've given you the graph in red, y equals 1 over x, and we're going to find the point, so the slope of the tangent at the point where x is equal to 1/2, and I've drawn that tangent line in for you right there, and we're also going to find the equation of the tangent line. Keep in mind that finding the slope of the tangent line is the exact same thing as finding the instantaneous rate of change of 1 over x when x is equal to 1/2. So to find that slope, we of course use the formula that it's the limit as h approaches 0. I'll actually write the original formula, a plus h minus f of a, all divided by h. So that's the formula that gives you the instantaneous rate of change at x equals a. Okay, now our a value is a half. So we want the limit as h approaches 0 of f of 1/2 plus h minus f of a half, all divided by h. Now we have one small technicality here, and that's the fact that there is no f of x in this question. There's a y equals, so we can solve that pretty simple. We can just say let f of x equal y, or let y equal f of x, so that we can deal with function notation as opposed to, y equals kind of notation. Okay, another thing I should probably notice is I need to know what f of a half is. So f of 1/2 is equal to, I shouldn't just use the graph, it's 1 over 1/2, 1 divided by a half, which is equal to 2. So there's that point there, is that 1/2 comma 2. Okay, so continuing, this is h, this is 2, and 1/2 plus h. So f of 1/2 plus h says replace x with a half plus h. So it's actually 1 over x plus h, sorry, 1/2 plus h. Let me just fix that. Just like that there. Sorry, that's kind of a mess. Let me just, there, that looks a little bit better. So we're dealing with 1 divided by a half plus h minus 2 all over h. And we want h to be as small as possible. Now again, notice that you can't plug in h equals 0. If you plug in h equals 0, you get 2 minus 2, which is 0 over 0. So you need to try small values. Like I said, later on, we're going to look at how we can do this algebraically. We don't need how we can do it without subbing in a small value. But for now, just so we understand the process, let's try some small values. So I'm going to start with h equals 0.1. What do I get? I get m equals negative 3.33. Okay. Let's try h equals 0.01. Let's go a bit smaller. When I do that, I get negative 3.92. Kind of a significant difference between those two numbers. When you first see negative 3 1/3, you might think it's exactly 3 1/3, or maybe it's negative 3.5, but all of a sudden it jumps and it's looking like it's closer to negative 4 right now. Let's try the other side. Rather than trying positive h values, let's try negative 0.01. If we do that, what do we get? By the way, all I'm doing to do this, I'm just pausing the video and I'm just using my calculator. I'm plugging in h equals, in this case, 0.01. A half is really just 0.5. So let's do it with negative 0.01, see what I get there. When I do that, I'm getting negative 4.08. So I think from that, there's no real good way, notationally wise, this is really weird because like this part right here, we're not going to do this very often. We're going to have a better way to look at this expression later on, okay? So for now, I'm just kind of writing when h equals, then this is what I get. When h equals, then this is what I get. When h really is just supposed to be a number that approaches 0. But in any case, I think you can clearly see here that the slope of the tangent looks like it's approximately negative 4. Which is between negative 4.08 and negative 3.92. Yes, it's exactly halfway between. That's a coincidence. It's not a coincidence, but that's because 1 over x is a pretty simple graph. Okay, that will not always be the case. It doesn't always work that way. With quadratics and simple graphs like 1 over x, that is true, but you have to be careful in general that you just can't do that every single time. So there we have it. We know the slope of this curve, or sorry, the slope here of this tangent line is negative 4. We're going to assume that that's true. And we're going to now find the equation as well. So to find the equation of the tangent line, of course, we have a slope that's equal to negative 4, and we have the point 1/2 and 2. So we can say that negative 4 will equal y minus 2, all divided by x minus a half using that point slope form. I'm going to cross multiply, okay, and I get negative 4x. Negative 4 times negative half is 2, plus 2 equals y minus 2. From there, I can put it in y equals mx plus b form or standard form. I think I'll go standard form, so I get 4x, okay, negative 4x minus y plus 4 equals 0, but I do not want the starting number to be negative, so instead I multiply by negative 1. And there you have the equation of your tangent line as well. There's some questions from the calculus book for you to work on. I believe most of these are just doing the same thing you did here, finding the slope of the tangent, find the equation of the tangent. I believe they all work out nicely. And when I say work out nicely, I mean you should be able to pretty confidently determine like this value right here. Yeah, although you're guessing and checking, you're probably going to be able to guess and check the correct number. That is the correct number, by the way. The slope of that line is exactly negative 4, and pretty soon you'll know how to calculate that yourself too. Okay, that's it. Thanks.